this is Tanya. I'm one of the TAs assigned to the Aircraft Stability Control course. We'll go over the questions of week 7. I think there was some issue with yesterday's session, although I have uploaded the slides and I'm trying to upload a recording. I'm not sure how much of it was recorded successfully. If not, we'll still have last year's lecture uploaded. So let's proceed with this session. So we'll just recap what we've learned. So hinge moment was a concept that was introduced I think a couple of weeks ago. What was hinge moment? The moment that the elevator or any of the other control surfaces produce above the hinge. So if your tail is something like this and your elevator is here, this is the point about which it is hinged. So that is the hinge point. Now upon deflecting the elevator down or when it's subject to some angle of attack, it produces some lift. And this lift produces a moment about the hinge, which is known as hinging moment. Now, similar to all the other moments that we've studied, it follows a similar form where CH is the hinge moment coefficient. And the hinge moment coefficient here, the linear form, is given below, where it depends on angle of attack at the tail, elevator deflection, and trim tab deflection. Now all of these coefficients, that all of these derivatives, we saw last time that all of them are negative. CH alpha tail, CH delta E, CH delta T, they are all negative. How? I think a couple of things that we've seen. Now let me just draw this. If I were to deflect my elevator down, if I were to deflect my elevator down, what happens is that it increases the effective camber of the tail of the cross section. It increases the effective camber. And when there's an increase in the camber, there's an increase in lift. So there is a increase in lift. So delta L, positive delta L is there when you deflect. So when I deflect the elevator down, is it positive or negative? What was our convention? Downward deflection of elevator, is it positive or negative? According to our convention, downward deflection of elevator was positive or negative? So according to our convention, downward deflection of elevator is positive. Okay, so for a positive deflection of elevator, there is a positive lift that is generated, and due to this positive lift, the moment at the hinge is negative. So your anti-clockwise moment we had studied was negative, right? So hinge moment. So for positive delta E, negative hinge moment. Similarly, if your tail is subject to positive angle of attack, tail is subject to positive angle of attack, again you have, so this is positive alpha tail, again you have an increase in lift, and again you will have a negative hinge moment. So if I have positive alpha tail, gives you negative hinge moment. Similarly, trim tab is another freely floating surface at the end of the tail. So you have something like, this is your tail elevator, and you have another surface here which is freely floating, and it follows the same convention as the elevator. When I deflect it down, or when it is deflected down, it's freely floating, so we are not really deflecting it. So when the trim tab is, if it is deflected down, if it is floating downwards, it is positive delta T, positive delta T. Again it produces an increase in lift, and this again produces a negative hinge moment. Anti-clockwise hinge moment, which is negative. So positive delta T also gives you negative hinge moment. So what this tells us is that all of these coefficients, that is CH alpha tail, which is dCH by d alpha tail, is negative. CH delta E is negative, and CH delta T is also negative. So all of these coefficients are negative. Okay. Alright. So this is your linearized equation for your coefficient of increment CHS CH0 plus or the dependent terms on alpha tail, delta E and delta T. Now to find out at what angle your elevator will float freely, what we have to do is to set this CH to be 0. Now assuming that there is no trim tab and it is a symmetric FL, so CH0 is 0, if you make these assumptions, then the equation that we get for delta E when we rearrange the terms, delta E float or delta E freely floating is given by minus CH alpha tail, CH delta E and directly proportional to alpha tail. Now if my tail is subject to a positive angle of attack, what will be the delta E float? Positive, negative, 0, what will it be if the tail is subject to a positive angle of attack? That is, if alpha tail is positive, what will it be? If alpha tail is positive, what will delta E float be? Positive, negative, 0. Negative, yes. So CH alpha tail and CH delta E are both positive, both negative, and alpha tail is positive, so your delta E float will be negative. So does that mean the elevator will float upwards or downwards? If I get delta E freely floating as negative, does that mean my elevator floats upwards or downwards? We just discussed the sign convention, right? So is it upwards or downwards? Upwards, yes. So according to a sign convention, if the elevator is floating, if it's negative, then it's floating upwards. Yeah. So yeah, this we just saw, all three are negative. So, and the equation, so this is for the stick free and the stick fixed case. So stick free is when your elevator is allowed to float freely. The slope of the CM versus CL graph. The slope of the CM versus CL graph is negative, but it has an additional term here. Now so this is negative, and the second term, is it positive or negative? Just look at all the individual components of that term and let me know if it's positive or negative. So BH is positive or negative? Horizontal tail volume ratio. Is VH positive or negative? What is VH? Yeah, so horizontal tail volume ratio, that's positive. This is positive. Eta, is it positive or negative? Tail efficiency factor. Positive, yes. This is also positive. CL alpha tail and CL alpha wing, are they positive or negative? The slope of the airfoils of lift and tail and wing. The lift curve slopes are both positive, right? So this is also positive. What about this term, 1 minus dou epsilon by dou alpha? Epsilon is the downwash slope of the downwash. So the slope is always less than 1. So this entire term will be positive. What about tau, control surface effectiveness parameter? Yes, so that's also positive. It's in the range of up to 0.4, we've seen that. So it's also positive. CH alpha tail and CH delta E, we just saw both are negative. So this is also, this entire term is also positive. So basically this entire second term is positive. So does that mean the stick fixed case is more or less stable than the stick free? So suppose say this is about minus 10 and this is say plus 5. This is completely random numbers. This is not in the range. I'm just trying to get a feel for it. So if this is minus 10 and minus 5, your DCN by DCL free would be minus 5, right? So is the stick free case more stable or stick fixed case more stable? What was the measure for stability? What was the measure for stability? Negative slope, yeah. So more negative, more stable. So is the stick fixed case more stable or stick free case more stable? Stick fixed case is more stable, correct. So it's more, so what happens in the stick free cases are there's a positive term that's added into your equation which reduces the stability. The stick fixed case is more stable, right? Okay, let's go on to the next line. Yeah, so this was again some conventions that we had seen. The stick conventions, when you push the stick forward, this is a general convention. If the question says anything differently, it is different. So we had seen one such question yesterday. I'll repeat the question today. Okay, so stick forward is considered, stick forward push is considered positive. So what this means is that when you push the stick forward, it corresponds to more velocity. More velocity, if you need to maintain everything else same, you need to reduce your CL. How do you reduce your CL? You need to reduce your angle of attack, CL or lift, right? You need to reduce your angle of attack at the tail. What do you do for this? You deflect your elevator down. When you deflect the elevator down, there is an increase in a lift which produces a pitch down moment, and hence it happens like the angle of attack at the tail is reduced, you get less CL and more velocity. So that's how it works. So when I push the stick forward, my elevator is deflected down, which gives you less angle of attack at the tail. It increases the lift at the tail, reduces the angle of attack, and then so on and so forth. Alright. So this, I had stressed on this even last time. So delta E required, we know the delta E required formula. So it was delta E required for given CL trim. So it was delta E naught plus there was one static margin term here, right? So static margin by CM delta E into CL trim. So this static margin, you need to remember that it is the stick fixed static margin, not the stick free static margin. Okay, so when you use this equation, this should be the stick fixed case and never the stick free case. Alright. So now we are encountered by three conditions: that your elevator is already floating at the angle at which you require it to float at the for the required CL. So if it's already floating at that angle, the pilot need not apply any force. He need not push the stick forward or pull the stick backward. So stick force required is 0. It's neutrally stable. Now if your elevator is floating at an angle less than the elevator required, you need to pull the elevator. When I pull the elevator, the stick force required is negative according to our sign convention. And third and final case, when the delta E float is greater than the one that's required, you need to push your elevator down and your stick force required is greater than 0 according to our convention. So now the stick force is given by hinge moment into delta E by Ls into delta S. Hinge moment Hm, delta E is elevator deflection. What was Ls and delta S? I think we had gone over this, even sir has done this derivation. So what was Ls and what was delta S? So let me just try drawing it. So if this is your stick, and if I were to deflect it, so it will be something like this, right? So this length is Ls, length of the stick, right? So that is Ls. So it's still here. This is Ls. Just erase that. So yeah, that length is Ls. Now when I deflect it, there is an angle that's formed here. There's a deflection that's formed here, that is delta S. Alright, so this is Ls and this delta S. Now this derivation was done in the, I think, last week's lectures, where the stick force equation is derived in terms of K, A, all of these coefficients, right? So this is the big elaborate equation that was derived in the class. This will be used in the assignment questions. We'll just go over them. Meanwhile, just before that, this was a question that I had done yesterday, but I think there was some issue, people were not able to join, so I'll just go over this question again. I thought it was relating to experimental data, so you get a proper feel of all the things that we've learned. So we'll just try doing this again. For an airplane, the wing loading is given to you, W by S, 400 Newton per meter square, flying at an altitude where density is 0.8 kg per meter cube, and this is what is recorded. Okay, so it was flown at 3 different velocities and 2 different CGs. So initially the X CG was 0.2, X bar CG was 0.2, and then it was 0.25. So these were the 2 CGs, and flown for 3 different velocities. And these are the stick forces required. So this is, say, Fs1 and Fs2. So for the first case, for the first CG, how much stick force is required to trim the aircraft at 3 different velocities, that is 50, 57.3 and 70.71 meter per second. And for the second case, how much stick force is required. Now in this question, it's explicitly given that pull is considered positive. Alright, so this will be plus 2, this will be plus 2, 0, 0, sorry, plus 1, this is negative 4, negative 2. Alright, so this is the data that's given to you. Now they've asked us to find the stick-free neutral point. Can you take a moment or two to come up with how do you solve this? So before that, how was neutral point and stick-free neutral point, how are they defined? What was neutral point? How was it defined? What was the definition of neutral point? Stick fixed and stick free. How was neutral point defined? Forget stick fixed and stick free. How did we start with the definition of neutral point? It's the point about which, so pitching moment is independent of angle of attack. So it's the same as aerodynamic center. Aerodynamic center is defined for a wing or a tail or some aerodynamic surface. The neutral point is the same definition but for the entire aircraft. So point about which your pitching moment is independent of angle of attack. So what about the stick-free case? It's a similar definition, but what we had seen mathematically was that dfs by q by dcl equals 0. So this was the definition for stick-free neutral point. So they've asked us to find the stick-free neutral point. So how do we go about doing this question? We have fs1, we have fs2. We need to find out the point at which dfs by q by dcl is 0. So take a moment or two to try and come up with the steps to solve this. So this is how the stick-free neutral point is obtained from experimental data. So just try to dfs by q, I'll just write it neatly. So it's dfs by q by dcl should be 0. This is how your stick-free neutral point is defined. So we need to find the point, the CG, at which dfs by q by dcl is 0. So what could be the steps that we can follow to get this value? we need to find out first. We need to find out all of these terms, right? So Fs by Q, Cl, all of those. So how do we find out Q? Q is the, what was Q? What was Q? Not the pitch rate. This was in terms of Cl. So Cl is half rho V square S Cl, right? So this dynamic pressure was Q, right? So in this case, Q is dynamic pressure. So half rho V square. So half rho V square. Okay, just a second. Just a second. So Q is half rho V square. It comes from this half rho V square SCl, right? So we can get Q from this equation. Similarly, you can rearrange the terms to get Cl. So let's just make two columns here for each case. Let's find out Q and Cl. So let's start with that. Then we'll do Fs by Q, Fs2 by Q. So I just make two more columns here. I'll just rewrite this. So we need to fill up these four columns. Is Q 100 or 1000? I think I'm getting 1000. Yeah. Yes. 1000, right? Yeah. Okay. Sorry. We have to find out CL, not lift, just CL. Yes, yes. There will be one S also. So in this case, the wing loading is directly given. So you can assume wing loading to be the L by S. So 400 by Q will give you CL. So that's 0.4. Second Q, right? This I'm just getting the double, and this is 0.2. Let's just verify these values and then we can solve them together. So I hope all the values are correct, so we can proceed from here. So now that we have fs1 by q and fs2 by q, let's try plotting it. So let's just make I'm just going to make a rough plot, but you can make a better plot. I'll also show you how you can do this on MATLAB or any other programming language. So let this be fs by q and let this be cl. So for cl of 0.4, what is fs1 by q? 0.02. So let's just CL of 0.4 is 0.002 and 2 is 0.003. So let's just join the corresponding lines. I should have taken another color, but it's something of this sort, right? So you get two lines. This is the first one was okay. Let me just see which one corresponds to which one. 0.4, 0.02. Yeah, so this is fs1 by q and this is fs2 by q. So you have two slopes, two equations, right? So what we need now is this dfs by q by dcl should be 0. So we need to find out the two slopes. We have two lines with two different slopes, and we need to find out the two slopes and then find out another graph. So let's just find out the two slopes. So it's dfs1 by q by dcl. What would it be? The slope of the first line. Let's take another color. So slope of the red line, and then we'll find out the slope of the blue line. Slope of the red line is, you can just take the 2 points. We have 3 points, but you can just take the first first and the last point for simplicity. y2 minus y1 by x2 minus x1. It's just the slope of the line, the straight line. So I'm getting 0.02. What about the blue line? dfs2 by q by dcl. Both are positive slopes, let's say. You just tell me what the slope of the second line would be. Just take the first and the last point. So it will just be 0.01 minus of minus 0.001 by 0.4 minus 0.2. Now what we have to do is to plot this with respect to CG. So we need to find the CG location at which dfs by q by dcl becomes 0. Right? So we need to plot that. So this dfs by q by dcl, and here you have x bar CG. Right? So you plot these two values. So for CG location 0.2, let's just say this is 0.2, this is 0.25. For 0.2 it is 0.02, correct? And for 0.25 it is, so now you just extrapolate it and find the point at which, find the CG location at which it becomes 0. Alright, so now I'll just show you how we can do this using a programming language. I'll stop sharing this. I think you can see this screen. So it's a simple code that I've written. So I've just defined all the velocities, 3 velocities that we have. This is in MATLAB. I'm not sure if you're familiar with MATLAB, but it's a language that we use for plotting these graphs and all of that. This is simple code. You can use any languages. I just thought we should also know this. So I found out the Q using half rho v square. CL is the wing loading divided by the half rho v square, or divided by q. We could have done that directly. The fs1, fs2, which is given in the question, I've taken it directly, and this is just the 2 columns. It's just used to fill up the 2 columns. Now what I will do, first figure will be between CL and the 2 fs by q's. Alright, so let's just run this and see how it looks. So this is the first figure. So you can see the line in red. Okay, so it's the reverse sign convention of what we had followed. So we have the 2 slopes here. So dfs1 by q and dfs2 by q. So you can see the 2 lines and the 2 slopes. The change here is that it's for different CGs. Okay, and then you plot the slope with respect to the CGs. Alright, So the figure 2 is CG and the individual slopes. Okay, so I'll just run it again. So this line is similar to what we have done in the rough figure. So you can see that it has a negative slope and it becomes 0 at point 0.3. You can use your simple straight line equation to find out the location at which this y-axis becomes 0. Okay, so y coordinate becomes 0. So it's a simple straight line equation. You can just plug in the values. You have the 2 points, find out the third point. You can also use a software to do this. So we can see that at CG 0.3, the slope is becoming 0. So the stick free neutral point is 0.3. Alright, I just thought we should see this once. Now let's go back to the slides. So these were the questions of week 7. So let's just go over that. So what was given to you? I think it's not the exact same question. It's a similar question. The values are slightly different. So let's just try solving this. Consider the following airplane in prop off condition being tested in a wind tunnel. So CG is 30% of mean aerodynamic chord. Weight is 700 kgs. So they're giving you the aspect ratio of the wing, wingspan, mean aerodynamic chord of the wing, aspect ratio of tail, tail span, alpha naught. That is, what is alpha naught? It is when the alpha at which lift is 0. The wing setting angle, tail setting angle, lift curve slopes of the wing and the tail. You have the distance, the moment arm LT, elevator area, elevator chord, elevator effectiveness parameter, that is tau. And then you have gearing ratio, which will come for your stick force Fs. In the big equation you had gearing ratio, and then you have your 3 derivatives, that is Ch delta E, that is variation of the hinge moment with respect to delta E, delta A, alpha tail, and delta T. You can see, like we had discussed, that all 3 of these derivatives are negative, right? Okay, so they've also given you this graph for the stick free and the stick fixed case, CM versus CL. We have seen that the stick fixed case is more stable. You can see that the slope is more negative in the stick fixed case. So it is corresponding to our what we had found out earlier. Okay, now let's look at the questions. What is the stick fixed neutral point in mean aerodynamic chord? So we just have to do this. We know the formula, it's minus dCm by dCl is x bar np minus x bar cg. So we have the graph, find out the slope, we have x bar cg, that's given to you in the question, right? Yeah, cg is 30% of mean aerodynamic chord. So we can just substitute the values in this formula and find out x bar np. So let's just try doing it for the first case, stick fixed case. So I'll just take the 2 points, minus 0.05 minus 0 by 0.3 minus, these are the points I'm taking, 0.8 is equal to x bar np minus 0.3 c bar. So just rearrange the terms and you can find x bar np to be 0.4 or 40% of mean aerodynamic chord. Now we can do it for the stick free case. It's the same formula, stick free case. So we'll take this point and this point. Only thing that will change is the slope. So minus dCm by dCl is x bar cg minus x bar np minus x bar cg. And this will be the stick free case. So yeah, it comes to 0.37, so it's 37% of mean aerodynamic chord. Okay. Next question is the wing area of the aircraft in meter square. So we have, this is the formula. So we have the aspect ratio of the wing. So this should be of the wing, of the wing, of the wing. Right. So you can just substitute all of the terms. Aspect ratio of the wing is 6. Span of the wing is again 6 squared upon S wing. So what do you get? S wing is 6. Next is, excuse me, what is the indicated trim airspeed for stick fixed case, taking density as given in the question? How do we go about doing this? Trim airspeed, just take lift equal to weight. Yes. On the data. All right. Yes, yes. Is this enough? Okay. Yeah. So for this, it's for the trim case. So you can just take lift equals weight and then proceed with the calculations. Sure, I'll just try doing it again. I'm getting 48. Let's just try doing this. So our formula is lift is half v squared S CL, and we need to find out v. Right? So this is equal to this. So under root 2w by rho S CL, that is under root 2 into 700 into 9.81 upon 6, and CL is 0.8, so I'm getting out 48.33. So let's go to the next question. So this is just the formula I've used. The tail volume ratio VH is. So VH formula was ST LT SC. Okay. Solve it for completion sake. So before we had found out this wing area, let's just do it for the tail also. So aspect ratio of the tail is span of the tail squared by ST. So ST squared by 4, and that comes as 1. So it simplifies our calculation. 1 upon, we have found out S as 6, LT is 6.5, and this is 1.2, so yes, 0.903. The value of Cm delta E in per degrees is, Cm delta E formula was minus eta VH Cl alpha tail into tau. So eta is given to us minus 0.9. VH we found out just now as 0.903. Cl alpha tail is given for the airfoil. We need to find it for the wing. So I just leave that for now, and tau is 0.4 is what I believe. Is 0.4. Now let's find out Cl alpha tail. Cl alpha tail for the wing is Cl is this for the wing alpha tail 2D by 1 plus Cl alpha tail 2D. So it's not alpha tail, it's alpha wing. Keeping in mind that they've asked you the answer in per degrees. You can take E as 1. So just try solving this. 0.1 plus 0.1 by E, PR of the wing, Really sorry, this is about this is the tail, right? So we're doing Cm delta E, so it should be Cl alpha tail. Right, so this will be 4. And they've asked you in per degree, so we can just directly convert it right here. Convert it right here after this. Okay, so that equation is valid only if it is in per radians. Cl alpha 2d has to be in per radians, correct? For this bottom part. Above you can leave it as it is because they've asked you in per degrees. So why we are converting it to per radians is that the Cl alpha 2d by pi EAR should be dimensionless. So if you have Cl alpha 2d in the denominator as degrees, then the dimension will not match, right? So Cl alpha 2d by pi EAR must be dimensionless. So the denominator Cl alpha 2d has to be in per radians. So I've just converted it by multiplying it by 57.3. 0.068 per degrees. Now I plug this in here, so it will be 0.068 and I'm getting minus 0.022 per degrees. Okay. So I hope this is clear. Let's go to the next question. Such the formula that we used. If the airplane was to be trimmed at an indicated airspeed of 200 kilometers per hour, find the tab setting required for CG location of 20% of mean aerodynamic chord. Okay. So let's just see what are the steps that we need to follow to get this. First, they've given you the speed in kilometer per hour. Always check the units. So our equations are valid for meters per second. So convert the speed first, and then we need to use the stick force equation. Now we need to find the CG location, find the tab setting required, but for that we need to use this this equation where we need to find out this delta t. Now in this equation, look at the unknowns that we have, right? So what we need to find is this delta t. You rearrange the equation to find out this delta t, and it is what are the unknowns in that equation. So I think it's taking time to load. Yeah, so I just rearrange the equation. We need to find out delta t. Now look at the unknowns in the equation and find out that. So what are the unknowns? A and dCm by dCl free. That we've already found out. So now you can just plug in these values into the delta t equation and find out the answer. Let's just start. So XCG is 0.3 minus X bar NP was X bar NP, X prime NP, we had found this, right? 0.37. So this is minus 0.37. So 0.07. Right? Then we need to find out A. So CH naught is 0. The CH alpha is 0.005. Alpha naught is minus 2. Bin setting angle is 0. Tail setting angle is 2. CH delta E is minus 0.007. And delta E is 3 degrees. Take delta E naught, right? 3 degrees. So how much is A? A comes to, correct me if I'm wrong, I'm getting minus 0.02. Okay, now that you know all of these, plug it into the main equation. What is delta T? Just write it here. Delta T is 2 into 700 into 9.81 by 6 into 1.225. I hope you've converted the velocities. So I'm getting 55.55 velocity square. Then 1 by CH delta T, that is minus 0.003. CH delta E minus 0.007 by minus 0. C delta E was 0.022. Then into this was minus 0.07. Minus of A was minus 0.02 by CH delta E is minus 0.003. Can you calculate and let me know what is the value that you're getting? I think I'm getting 3.885. You can verify this. I'm getting 3.85, but do let me know if it's wrong. Let's go to the next question. Calculate the DFS by dV for the CG location of 20% of mean aerodynamic chord. Okay, I think here, okay, they had said 20% of mean aerodynamic chord even in the previous question. So this is 0.2. So this comes to 0.1. Where is this, right? So that correction had to be made. Yeah. Calculate the DFS by dV for the CG location of 20% mean aerodynamic chord. How do we proceed with this? DFS by dV, we have the formula. So this is the formula where the only unknown is K. You can use the gearing ratio given in the question and find out DFS by dV. Gearing ratio is minus 1.5, elevator area 0.5, elevator chord 2.5, heated tail 0.9. This comes to minus 0.96875. When you plug it into this equation, I'm getting something around 0.37. You can verify this. So I think, yeah, with that we come to the end of today's session. Does anybody have any questions? Yeah. Yeah, these are the only two equations, that is Fs and dFs by dV. dFs by dV, I think you can still find the derivative, so you just have to study the Fs. We can't be sure. Yeah, so there are just a few of them. This Fs is the only one. You can just remember the Fs equation and then you can find the derivative. Similarly, for the other big equation that I thought was the pitching moment equation, but that is also very, if you try looking at it, it's very intuitive, so you can remember it or you can derive it. So I think the only big equation here is Fs. Thank you. So if there are no questions, then we can meet next Saturday. All the very best for your assignment. We'll meet again on Saturday. Thank you.